take a look at the board up here. There's two reactions listed. One of them is a fission reaction, and one of them is a fusion reaction. Tell me which one's which. First one?
Fusion.
Yeah, that's a fusion reaction. We know that because we have two light nuclei forming one heavier nucleus. It's 2 to 1. Now, we also have some other things here as well, right? The neutron and the energy, and those are really important as we learned yesterday, but they're not important to determining what type of reaction we have here. Two things become one. They are fusing together to become one. That's a fusion reaction. Now, the second one must be fission then, and it is fission. We know that because we have one thing becoming two things. And again, we have the neutron on the one side and sometimes 2, sometimes 3, sometimes 4 neutrons on the right side, depending on the reaction that's taking place. Some energy as well. And those are all important, but what's most important to determining that it's a fission reaction is that one thing becomes two. Now, there's energy released in both of these. Can you tell me which one would release more energy per individual reaction? Okay, the number 1, the fusion reaction, or number 2, the fission reaction. Per reaction, it would be, Patrick?
2.
It would be reaction 2, yeah. And instinct kind of tells us that, oh, it's got to be fusion, right? Fusion is way more powerful than fission is. Well, it is per kilogram, right? Per kilogram of fuel. If you're comparing apples to apples, we would say that nuclear fission is less powerful. Comparing energy per reaction, fission is more powerful, fusion is less powerful. But apples to apples, energy per kilogram of fuel, we would say that fusion is by far the most amount of energy, and fission is the least amount of energy. Now, if we were to add the chemical reaction in there, it's a completely different thing than what we're talking about, because that involves electrons orbiting around the nucleus doing their thing. Okay, we're not talking about electrons at all with fission or fusion. We're talking about just the nucleus. But if we were to add a chemical reaction in there, how would a chemical reaction compare in terms of energy per reaction? It would be third, yeah, it would be a distant third. And in terms of energy per kilogram of fuel, it would also be a distant third, no matter what the chemical reaction is. Now, what about the byproduct risk? If we get fission, okay, that's where one thing breaks up into two. An example that I gave you a couple times, uranium-235 breaks into krypton and baryon and 3 neutrons. What do we know about those products or those daughter nuclei? Yeah, they're radioactive, and that means they're bad. And the degree of radioactivity does depend upon the products that are produced. Sometimes you get krypton and barium, sometimes you get 2 other products, whatever. So you can get different degrees of bad, but it's all going to be bad because the products are radioactive. Now, fusion reaction produces products that are relatively harmless. Basically, if you're not incinerated in the actual nuclear explosion, then the product of nuclear fusion will have decayed quick enough that it's not going to cause any dramatic lasting effects. Nuclear fission, byproducts of chemical reaction, by the way, just as an aside, they're all different, right? Sometimes, depends on the reaction, sometimes they're really, really good. Okay, the byproduct of a chemical reaction of cooking steak, which is a chemical reaction, is a really, really good reaction. The byproduct of some other reaction might be poisonous to you. So we can't really compare a chemical reaction in terms of the risk of their byproducts. All right, I wanted to find 2 terms for you now. This is new, and this is where these reactions, these fission and fusion reactions, get their energy from. Nobody's questioned that so far. We said in both of them we produce energy. One produces more per kilogram, one produces more per reaction, but nobody's questioned where the energy actually comes from. Well, it comes from something that we call the mass defect. And we're going to define mass defect in 2 different ways. One in the context of a single nucleus. That's the most fundamental definition of the mass defect. And the other is going to be in the context in the context of a reaction, a fission or fusion reaction. Let me give you an analogy here to help you kind of lead you into this, okay? Let's say there's 20 people in this room right now. I'm not sure exactly how many people we have, but let's say there's 20. And let's say, just for ease of argument, that every single person weighs exactly 50 kilograms. So you weigh 50 kilograms, you weigh 50 kilograms, you weigh 50 kilograms, you weigh 50 kilograms, and you weigh 50 kilograms. Everybody weighs 50 kilograms. Got it? So we have 20 nucleons, 20 different protons and neutrons that make up this class, right? It each weighs 50 kilograms. What's the mass of the nucleus? We have 20. Each one weighs 50. What's the mass of the nucleus? It's 1,000, right? 20 times 50 is 1,000, but it's not. It's 998.4. The mass of the nucleus is less than the mass of what makes up the nucleus. The mass of the nucleus is less than the mass of the nucleons. That's the first way we define the mass defect. That's a crazy concept. It's a crazy concept. And the way that can happen is by an energy thing, right? As opposed to all of the mass being mass, some of the mass ends up being energy. Okay? Energy that's stored in bonds here. So we're going to say that in the context of a single nucleus, like carbon-14, the mass defect is the difference in mass between the 14 nucleons that make up carbon-14 and the carbon-14 nucleus itself. The mass of the nucleus will always be ever so slightly less than the mass of the nucleons. Right? The mass of this class, we think it should be 1,000 kilograms, but it's only 988.4 kilograms. The mass of the nucleons is 1,000. The nucleus is only 998.4 kilograms. Now, in the context of a fission or fusion reaction, we have what we sometimes call reactants and products. The reactants, or the parent nuclei, have a certain mass. When this reaction, this nuclear reaction takes place, some of that mass disappears. It's gone. And it happens because of the difference in mass between the nucleus and the nucleons. In other words, the mass defect in the context of a single nucleus leads to the mass defect in the context of a nuclear fission or fusion or any other nuclear reaction. What we find in this reaction is that the daughter nuclei, or the products end up weighing a little bit less than the reactants. Okay? Now, where does that mass go? Didn't you guys learn in like grade 8 or grade 9 something called the law of conservation of matter? Matter can't be created or destroyed. Like, you got a certain amount of matter, it's always going to be matter. Didn't you guys learn about something like that? Yeah, chemistry, you talk about, like, you may not explicitly state that, but in chemistry, it's assumed that the amount of matter stays the same, right? You have 6 carbons on this side, you have to have 6 carbons on the other side. Okay, matter stays the same, matter is conserved. Well, the truth is it's not. The truth is, in a nuclear reaction, matter can be completely gone. But it doesn't just get completely destroyed, rather it gets converted to energy. Call it binding energy. The binding energy is the energy equivalent of the mass defect. So if you were to take the mass defect in a nucleus, you could calculate the amount of energy that makes up the difference. Does that make sense? You got a certain amount of mass, you got a certain amount of, like the mass of the nucleus is this, the mass of the nucleons is this, the difference is the mass defect, which is stored in the energy form. You could find the value of that energy by multiplying, well, I won't tell you right now, I'll tell you in a second. Now, the binding energy in the context of a reaction is the energy that gets released in the reaction. It says the energy that gets released from reaction, if the binding energy is still available after the reaction. Listen, remember this, the energy that gets released in the reaction. How do we find it? Well, again, it comes from this mass defect. How do we calculate the binding energy from the mass defect? Take a wild stab at this. How do you calculate the binding energy, the energy that's released in the reaction, from the mass defect? Yep. E equals mc squared. Okay, so take the mass defect, multiply it by c squared. C stands for what, by the way? Speed of light, 3 times 10 to the 8. Square it, and you get the binding energy. Now, I'm going to give you a couple of units here that you're not going to be familiar with probably. In my opinion, it's very unlikely that you will ever need to use these in Physics 30. They're not explicitly mentioned in our Physics 30 curriculum, but they are given to us. They are listed on our data sheet. So I'm going to tell you what they are, just in case. I don't expect them to appear, but because they're on our data sheet, you never know. Okay, I want you to be ready for it just in case. The good news is it's not all that hard. An atomic mass unit and an MeV per c squared are both units of mass. They both measure mass, like a kilogram or a gram measures mass. And on your data sheet on the left-hand side, you can see that an atomic mass unit is equal to 1.67 times 10 to the minus 27 kilograms. So they give you a conversion factor for an atomic mass unit. If you're ever given that something has 4.3 atomic mass units, convert it to kilograms and do your thing. Just get it in kilograms and do your thing. Now, how do you do the conversion? Just like with electron volts to joules, we would say 1 atomic mass unit over 1.67 times 10 to the minus 27 equals, 4.3 atomic mass units, whatever you're given, over x. And x would be the amount of mass in kilograms. So if you are given atomic mass units, just go to the left-hand side of your data sheet, convert it to kilograms, and do your thing. So you do whatever you would do with that mass. Don't panic about it. I don't expect you'll see it, but even if you do, don't panic about it. Just convert it to kilograms and do your thing. Now, an MeV per c squared is a little more awkward of a conversion. It's not crazy hard. It's just a little bit more awkward. If you look at the right-hand side of your data sheet, everybody pull out your data sheet right now. If you look on the right-hand side of your data sheet, you can see MeV per c squared used down close to the bottom. We'll talk about these first-generation fermions, quarks, and so on. We'll talk about those on the Wednesday we get back after Christmas break. Okay, but you see, whatever those quarks are, you can see that the mass is given in MeV per c squared. Now, we're not actually given a conversion factor to kilograms from MeV per c squared, but we kind of are. If you look closely, it says the mass of an electron is 0.511 MeV per c squared, right? The mass of the electron and the mass of the positron is that as well, because positron is the same as an electron except for the charge, right? There's the mass of the electron. But it also tells us a few lines above, the mass of the electron is 9.11 times 10 to the minus 31 kilograms. So it doesn't explicitly state that this is equal to this, but in one place it says it's 0.511, in another place it says it's 9.11. So let's set those equal to each other. And then, if we need to convert MeV per c squared to kilograms, let's just do a conversion using a ratio here. 0.511 MeV per c squared over 9.11 times 10 to the minus 31 equals, well, however many MeV per c squared you have, let's say 3.64 MeV per c squared over x. And x would be equal to the mass of whatever 3.64 MeV per c squared is in kilograms, right? Again, I don't think you're going to have to do that. I doubt you'll have to do that. I'm 95% sure you're not going to have to do that. But just in case, now you've got a fighting chance at doing it. Okay, you know that when you're doing a calculation with mass, you should be in kilograms. So whatever you're in grams, convert to kilograms. MeV per c squared, convert to kilograms. All right, we're going to do 2 examples today involving mass defect / binding energy, and then we're going to call it a day, we're going to call it a week, we're going to call it a year, and then we'll just see you next year, I guess. Pick up on this where we left off next year. Determine the binding energy in the following nucleus. So this is in the context of a single nucleus. Binding energy comes from what? Binding energy, a 2-word phrase, comes from what? Another two-word phrase. Mass defect. So what we want to do first is find the mass defect and then multiply mass defect by c squared. Let's get the mass defect. In the top right-hand corner of your example question booklet that I gave you on the first day of this unit, you've got a bunch of different masses, including the mass of barium-141. The mass of that nucleus, so let's actually change that. Let's say the mass of the nucleus, it's given to us here as 2.339179.239 times 10 to the minus 25 kilograms. That's a lot of significant figures, but because the mass defect won't be very high, we want to use a lot of significant figures. We could probably get away with less than this, but we'll use that. Okay, now let's find the mass of the nucleons. Not nucleus, the nucleons. We have 56 protons. So let's multiply 56 by the mass of a proton. It's 1.67207816 times 10 to the minus 27 kilograms. When I multiply those together, that gives me 9.363637,696 times 10 to the minus 26 kilograms. So there's the mass of the protons that make up the nucleus. Now we've got to find the mass of the neutrons. How many neutrons do we have here? 141 minus 56 is 85, yeah. We have 85 neutrons. We've got to multiply by that by the mass of a neutron, which is almost the same as the mass of a proton. 1.6743839 times 10 to the minus 27 kilograms. When we multiply those together, we get 1.42322,632 times 10 to the minus 25 kilograms. Let's add these up. That's going to give us the mass of the nucleus, the nucleons. Would you expect that number to be greater or less than the mass of the nucleus? The mass of the nucleons is always going to be slightly more than the mass of the nucleus. In this case, it's 2.35959008 times 10 to the negative 25 kilograms. Remember, the mass of 20 of us at 50 kilograms should have been 1,000, but the mass of the class was only 998. So the mass of the nucleus is a little bit less than the nucleons. Okay, there we go. We're not done. We don't even have the mass defect. The mass defect is the difference between those two numbers. 2.35 minus 2.339179.239 times 10 to the minus 25. I'm sorry? The mass of the nucleus, the nucleus, this is smaller than the mass of the sum of its parts. If you add up the mass of everybody in the room, it's 1,000, but it only equals 998. So the mass defect here, when we subtract those two, is 2.04108,456 times 10 to the minus 27 kilograms. And now finally, how do we find the energy, the binding energy? What makes up the difference in the mass? E is equal to mc squared. So we take that value that we just got, we multiply it by the speed of light squared, and we end up getting 1.84 times 10 to the negative 10 joules. Sometimes that's given to you in electron volts, or your answer needs to be expressed in electron volts, but you know how to convert joules to electron volts now, right? Just do that ratio. It's on your data sheet. Okay, there's quite a bit of numbers here, but in principle, this is not very hard. Get the mass of the nucleus. That's given to you. Get the mass of the nucleons, the protons and neutrons. Okay, 56 times the mass of a proton, 85 times the mass of a neutron. Add those up, get the mass of the nucleons. And then subtract those two numbers. Subtract this one from this one to get the mass defect. And then just multiply it by c squared. The next example we're going to do is not in the context of a single nucleus, rather it's in the context of a reaction. So the mechanism by which we're going to do this is slightly different, but the basic process is the same. Get the mass defect, then get the binding energy. Got it? Those are the steps. That's how you always do it. Get the mass defect, get the binding energy. Here we get the mass defect by doing what we did, right? Subtracting the mass of the nucleus from the mass of the nucleons. In the next example, we're going to get the mass defect in a different way. But we're still going to get the mass defect, and then we're still going to multiply that by c squared to get the binding energy. Okay, let's do this one now. Again, these numbers, the numbers that you'll need are in the top right-hand corner of your data sheet, or sorry, of the example question sheet that I gave you. This is a question on a test. These numbers are going to be given to you as well, right? Although they're probably going to be buried in a page of information, but they'll be there. You just gotta find them. Determine the energy released in the following nuclear reaction. Let's get the mass of the, let's call it the parent, or let's call it the reactant. Mass of the reactants. Let's get the mass of the products, or the daughter. Let's subtract them to get mass defect, and then E equals mc squared to get the energy. So you just need the mass defect. Whenever you're looking for the energy, get the mass defect, and then get the binding energy. How do we get the mass defect here? Well, let's get the mass of both sides. A neutron has a mass of 1.67. Here, it's a lot of numbers, so let's start over here. 1.6743839 times 10 to the minus 27 kilograms. The mass of uranium-235 is given to us as 29238 times 10 to the minus 25 kilograms. We add those up to get the mass of the reactants, and we end up getting 3.91. I'm going to assume you guys can do this math. 918,473,077 times 10 to the negative 25 kilograms. So the mass of our reactants. Now let's get the mass of our products. Krypton has a mass of 1.5259741896 times 10 to the minus 25 kilograms. That's on, again, in the top right-hand corner of that page. Barium has a mass of 2.339. 179,239,2 times 10 to the minus 25 kilograms. And then the neutrons, there's three of them. In order to balance this equation out, there's three of them. 3 times 1.6743839 times 10 to the minus 27 kilograms. Add those up. We get the mass of the products to be 3.91538494458. Holy cow, times 10 to the minus 25 kilograms. Notice the mass of the products are ever so slightly less than the mass of the reactant. What do we call the difference in mass? The mass defect. Let's get the mass defect. By this time subtracting the mass of the products from the mass of the reactants. Last time, remember, we got it from subtracting the mass of the nucleus from the mass of the nucleons. This time it's mass of the products from the mass of the reactants. When we do that, we end up getting 3.0881312 times 10 to the negative 28 kilograms. And then finally, finally, here's the easy part. You want to find the energy from that mass defect? What do? Times it by c squared. E is equal to mc squared. So take that number, times it by 3 times 10 to the 8 squared. And when we do that, we get 2.78 times 10 to the negative 11 joules. So the energy released in this particular fission reaction in one single reaction is 2.78 times 10 to the negative 11 joules. Not very much energy, right? 10 to the negative 11 joules. Well, remember what we said? We said yesterday, that's enough energy to maybe move a speck of dust. You need this to become a chain reaction if you want to move lots of specks of dust, right? So you need this energy to grow exponentially.